Small sample hypothesis test. Example 4. Example 4a. In a sample of n equal 3 light bulbs, the proportion of defectives p hat 1 out of 3. In order to meet industry standards, the proportion of defectives must be less than 0.1. And the proportion of good light bulbs, so that's represented by the letter P. Proportion of good light bulbs, Q, is going to be 1 minus P, which would be 0.9. So we want at most 0.1 defective and at least 0.9 that are good. So we want to test the hypotheses at the alpha equal 0.05 level of significance. H naught, P is equal to 0.1, the company does not meet the standard, versus H1, P is less than 0.1, the company does meet the standard. So this is a left-tailed test. And again, we want to check whether n times p is at least 5 and n times q is at least 5. If so, then we can use the z-table as a shortcut for testing the hypotheses. Otherwise, we need to use the exact binomial probabilities. So we're going to, we don't know what p is, but we're going to put in the value of p as if h naught is true. So, so our sample size is 3. So, and if h naught is true, then p should be 0.1, and 3 times 0.1 is 0.3, greater than or equal to 5, and that's a no. And then n times q would be 3 times q is 0.9, 0.9, 2.7, greater than or equal to 5, and that's a no. So if we get no, or no, yes, or yes, no, then we have to use the exact binomial probabilities. If we get yes, yes, then we can use the z-table to compute the approximate probabilities. These are called binomial because there's two possible outcomes. Either the light bulb is good or it's not good. It's a random variable because a different 3 light bulbs might have a different number of defectives in it. So the number of defectives can vary randomly from one sample to another. So we're going to want to make a tree diagram as if h naught is true. So we set up the tree diagram as if each light bulb has a 0.1 chance of being defective and a 0.9 chance of being good. Okay, so let's do the tree diagram. Okay, so I'll make these good and bad because or bad. Let's do bad and good. I'll say bad. Defective has too many words, and I'm trying to fit it into the space here. And good. So if h naught is true, they have each light bulb has a 0.1 chance of being bad, a 0.9 chance of being good. So the first light bulb, either bad or good. There's 2 possible outcomes. And second light bulb, also either bad or good. I'll just put B and G. And probability 0.1, 0.9. So with 2 light bulbs, there's 4 possible outcomes. They can both be bad. First is bad, the second is good. First light bulb is good, the second one is bad, or they can both be good. So each time you add a light bulb, the number of possible outcomes doubles. Third light bulb again can either be bad or good. Okay, so and the probability 0.1, 0.9, 0.1, 0.9, 0.1, 0.9, 0.1, 0.9. Okay, so if we multiply 1 times 1 times 1 is 1, and we have 1, 2, 3 digits to the right of the decimal. So 0.1 times 0.1 times 0.1 is going to be 0.001. and that would be all three are bad. Okay, B, B, B. Okay, and then the next path, 0.1 times 0.1 times 0.9. Actually, want the paths where, one or fewer. Want the paths where one or fewer are good. So actually, we can skip. One or fewer are bad. So we can actually skip this path here. Skip, because we have 4 bads. So we can skip this path here too. Skip this one here. We only need the paths where we have 1 or fewer bad. So let's do this path here. We have 0.1 times 0.9 times 0.9. So 1 times 9 is 9, times 9 is 81, and we have 3 digits to the right of the decimal. So it's going to be 0.081. That's bad, good, good. And then we have good, bad, bad. We can skip. Good, bad, good. That's 0.9 times 0.1 times 0.9. That's going to be 0.081. And that's good, bad, good. And then next path, good, good, bad. Again, that's going to be 0.081. Good, good, bad. And then the last path, 0.9 times 0.9 times 0.9. It's going to be 0.729. That's good, good, good. These are the paths where 1 or fewer are bad. Okay. So either one bad or none. Okay, so if we add these up, we'll get the p-value. 1 and 1 is 2 and 1 is 3, and 9 is 12. Carry the 1. 1 is 9, 17, 25, 27. Carry the 2. 2 and 7 is 9. So our p-value is 0.972, which is more than alpha. 0.972, greater than alpha, which is 0.05, and so we failed to reject H naught. There's not enough evidence. Sample does not provide enough evidence. Evidence to say that the company meets the standard. Okay. Not provide enough evidence. Okay. We can also put the same information in a table. Some of the problems in my lab ask you to put the information in the table, and we only need to list the paths where 1 or fewer were bad. So we have bad, good, good. The probability is if H naught is true, 0.1 times 0.9 times 0.9 is 0.081. Good, bad, good. Probability is 0.9 times 0.1 times 0.9, 0.081, and good, good, bad, probability 0.9 times 0.9 times 0.1, 0.081, and good, 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 0.9 times 0.9, 0.9, 0.729. Add these up. 1 is 2 and 1 is 3, 9 is 12, carry the 1. 1 is 8, 9, 17, 25, 27, carry the 2. 2 and 7 is 9. So we get the p-value of 0.972. And this is more than our desired level of doubt, which is 0.05. So we fail to reject H0. The sample does not provide enough evidence to say the company meets the standard of fewer than 10% defective. Okay. And we can also make a diagram like we did for some of the other examples of the possible outcomes of hypothesis testing. Either H0 is true or H1 is true, and either we don't reject H0 or we reject H0. Okay, if we reject H0 and H0 is true, that's called a type 1 error. That's represented by the Greek letter alpha. If we don't reject H0 and H0 is true, that's our confidence level. That's 1 minus alpha. If we don't reject H0 and H1 is true, that's called a type 2 error. And the probability of type 2 error is represented by the Greek letter beta, which is, I seem to have frozen here. Oh boy, I don't know. Okay, that looks like I'm not frozen. Type 2 error, and that's represented by the Greek letter beta that looks like a capital B, a script B. And if we reject H0 and H1 is true, that's called the power of the test. That's 1 minus beta. So 1 minus alpha, desired level of confidence. Greek letter alpha, desired level of significance. I like to call it that level of doubt. It's the probability of a type 1 error. P-value says here actual level of doubt, but more precisely it's the probability of getting a result this extreme if H0 is true. Greek letter beta, probability of a type 2 error. 1 minus beta is the power of the test. Because we failed to reject H0 in the above example, what type of error might we have been making? I'll give you a minute to think about it. So if you fail to reject H0, you're always taking a chance of a type 2 error. If you reject H0, you're taking a chance of a type 1 error. But here we fail to reject H0, so we make a chance of a type 2 error. So it's possible we made a type 2 error. Okay. Okay, example 4b. Redo example 4a if the proportion of defectives was 0 out of 3. And we can use the same tree, but now we only add the probability for the paths with at most 0 defectives. And there's only going to be one path with 0 defectives. So okay, so we'll make the tree as if H0 was true. First light bulb is either bad or good. If H0 is true, has a 0.1 chance of being bad, a 0.9 chance of being good. And then, so that's for the first bulb. Second bulb is also either bad or good. I'll abbreviate this B and G so I don't run out of space here. Probability 0.1, 0.9, 0.1, 0.9, second bulb. Okay, third bulb is also either bad or good. Third bulb. Probabilities are 0.1, 0.9, 0.1, 0.9, 1, 0.9, 0.9. Okay, so we want the paths with at most 0 defectives. So there's only one path. We can skip the top 7 paths here. We skip all these paths here. We only need the paths where we have at most 0 defectives. Okay, so we have 0.9 times 0.9 times 0.9, which is 0.729. And that's that path is going to be good, good, good. So our p-value is 0.729. 0.729. It's more than alpha, which is 0.05. So even with 0 defectives, because of the small sample size, even with 0 defectives, it's not going to give us enough evidence. Sample does not provide enough evidence. To say that the company meets the standard. Okay, the sample size is just too small, even with no defectives. So let's see what happens with a bigger sample. Example 4c, we do example 4a if the proportion of defectives p hat is 0 out of 10. Full tree would have over 1,000 paths, but we only really need one path. It's the path where all of the light bulbs are good. So this is a smaller tree here. We only have 3 light bulbs, but we only use, let's see, I'll use this one here. We only need the bottom path here where all the light bulbs are good because we have no defectives. So here's the that one path. Just to save some space, I made this path vertical instead of horizontal. So so if we multiply these together, we get a p-value of approximately 0.35. So even with 0 out of 10, our p-value is still more than alpha. Alpha is 0.05. So again, we failed to reject H0. The sample does not provide enough evidence. So let's try an even bigger sample. Without drawing a tree, find the p-value of the proportion of defectives is 0 out of 40. So you can maybe see the pattern here. With 0 out of 10, we multiplied 0.9 times 0.9 times 0.9, or 0.9 to the 10th power. This is going to be 0.9 to the 40th power. The p-value here, maybe you can see the pattern without drawing the tree, 0.9 to the 40th power. And you can do that on a calculator. It's a little too much to do by hand, I think. So you want to put 0.9 and then the exponent key. It looks a little bit like an arrow, and then 40, and then equals. I get 0.014 something. So it's say it's approximately 0.015 approximately. So this is greater than alpha, which is 0.05, and so so in this case we would reject H naught and conclude that that the sample does provide, that the company does meet the standard. So reject H naught and conclude company meets the standard. So we reject H naught with 95% confidence. Include the company meets the standard of fewer than 10%. Fewer than one, yeah, yeah, 10% defective. And that concludes this presentation.